Hello, Jeff Osborne again. We're back for another episode. Now that I'm a big famous YouTube celebrity, I think I need to do a little bit of hair and makeup. Today we're going to be talking about electric circuits and how they can be in series or in parallel. Looking at a real circuit board is very complicated with lots of different devices like batteries and resistors and switches. So what we're going to do is break it down piece by piece so that you can understand what to do. So first we're going to start off by learning some of the key vocab terms, such as voltage, current, resistance, and power. First off is voltage, which is measured in volts. The SI unit is symbolized by a capital letter V, basically equivalent to energy and also known as potential or potential difference. Next up is current, which is measured in the SI unit amps or amperes, symboled in the equations by a capital letter I. It is equal to the amount of charge that passes a part of a circuit per second, and current can either be AC, which is alternating, or DC for direct current. Then we have resistance, which is measured by the SI unit ohms, symbolized by the Greek omega symbol. And resistance is what limits the amount of current through a circuit, either due to imperfections in the wire or purposefully designed to create things like heat, or if you have enough heat, it'll start to glow and make light. The last word we're going to cover is power, which is measured in the SI unit watts, symbolized by a capital P. It is the rate which energy is converted, and it is the product of current and voltage. I know. Questions. How are these things related within a circuit? It wouldn't be physics class without a few equations. First one is Ohm's law, where the voltage equals the current times resistance, or V equals IR. Then we have Joule's law, which is power equals current times the voltage, or P equals IV. And then we have series circuits, or RS, being equal to the sigma or sum of all the resistors in the series. And finally, we have the parallel circuit, which is 1 over RP equals the sigma or sum of each reciprocal of the resistor in parallel. So here's some things you need to know about circuits so that we can apply the vocabulary and those 4 equations. First, we're going to work with series circuits. These are circuits that have multiple resistors along the same path of current flow. In those, the total resistance will increase, which causes the overall current to decrease, which ultimately decreases the amount of power produced. So I've built a 3 resistor series circuit from simulations from CB Boulder. And we're going to use those to see how different components affect the voltage or potential difference, the current, and how much power is being put out by that part of the circuit. So here's a battery. There's a switch that acts as light on and off. Then we've got a resistor, a light bulb, and a third component, another resistor, that will affect how this circuit behaves, all connected by wires that allow the electrons to flow through. So the first thing I'm going to do is click the switch. And as you can see, now we have some current moving through the circuit as the electrons move around from one side of the battery to the other. Notice the light bulb isn't very bright, which kind of has to do with the amount of power output. So I'm going to come over here and click the values button, I guess. And now you can see we have a 10 ohm resistor, 20 ohms through the light filament, a 30 ohm resistor, and our 12 volt battery. So the question is going to be, how does the amount of current compare as we move around the circuit? So if we go ahead and just take this ammeter and go to various parts, we'll notice that it has 0.2 amps. So it doesn't matter where I move it, everywhere in that circuit has the same amount of current. Now, the reason for this is kind of like traffic problems. So if you're backed up in traffic, it doesn't matter if you have an easy stretch of the road to go through. What matters is where it's blocked up the most. So this big resistor kind of slows down the current everywhere else in the entire circuit. So, constant current. The voltage, on the other hand, is going to drop different amounts in different places. Where it is easy to pass through, across this 10 ohm resistor, out of the 12 volts that the battery is producing, only 2 volts are used up or are required to get the electrons to go across that resistor in that rate. Well, the 20 ohm resistor is harder for the electrons to move through, and that takes 4 volts to get those electrons pushed from one side of the light to the other. 30 ohms is the hardest in the circuit, so we would expect the biggest voltage drop. And we have a negative number, which means I put the meter on backwards. So I'll switch that around. And there's the 6 volts that dropped. So if you remember, we had 2 volts to get across the 10 ohm resistor, 4 to get across the 20 ohm resistor, and 6 to get across the largest resistor of our circuit. Anywhere else through the wire, as an ideal conductor, no voltage to get across. So schematically, this is what this diagram would look like. And how can we use math to make those predictions so we know what we should get before it's ever built? So after seeing the simulation and realizing what the circuit's supposed to do, we need to explore the math on how it actually works. In the upper corner, we have a schematic diagram from our simulation. And to figure out the equivalent series resistance, we have to add up all of the individual resistors in that series. So we're going to add the 10, 20, and 30 ohm resistors, meaning this circuit works as if it had a total resistance of 60 ohms. We just calculated that the equivalent resistance for that series circuit is 60 ohms. So we'll do a new schematic diagram that has a single 60 ohm resistor in it. On the top line of our RIVP table, showing that resistance times current equals the voltage, and current times voltage equals power, we're going to fill in the things we know. We know there's 60 ohms of resistance, and we know the battery is 12 volts. Doing a little bit of math, we can figure out that the current is 0.2 amps, and the power, 0.2 times 12, would be 2.4 watts. Now, the real circuit didn't have a 60 ohm resistor, but it did have a 10, a 20, and a 30 resistor, so we put those into our table. Knowing that current is constant in a series circuit, all of those resistors have 0.2 amps of current. So we're going to write those into the table. Now, using Ohm's law, we can calculate the voltage for the 3 real resistors. 10 times 0.2 gives us 2 volts out of the 12 that were dissipated or dropped as it went across the 10 ohm resistor. 20 times 0.2 gives us 4 volts that were lost going across the 20 ohm resistor. And for the last one, we multiply across to get our remaining 6 volts being lost. Then, using Joule's law, we can go ahead and multiply the current times the voltage, I times V. 0.2 times 2 gives us 0.4, 0.8, and 1.2 watts of power used by each of those resistors in our circuit. Using the table, there's an easy way to check to see if you've got the right voltage and the right power in a series circuit. So we figured out that there were 6, 4, and 2 volts. If we add those up, we get to the 12 at the very top line from the battery. We can do the same thing with power, add 1.2, 0.8, and 0.4, and that'll give us the 2.4 watts that the entire circuit is used. Our numbers check out, so we did everything okay. Now that we've got series circuits figured out, here are some things you need to know about Working with parallel circuits. In parallel circuits, there are multiple paths for the electricity to flow through, but each only has a single resistor. This causes the overall resistance to decrease, which causes the overall current to increase, and it causes more power to be used. So I've constructed another circuit. This one's in parallel from CU Boulder's PhET simulation software. It's parallel because if you notice that we have multiple branches, we have a branch there, we have a second branch through here, we have a third branch for electrons to move around the circuit to get to the other side of the battery. So I'm going to go ahead and click the switches, and you can see this first light has a lot of power to it because it's really bright. Current moving through it pretty quickly and suggesting that there's low resistance within that particular light bulb. I'll click that switch, and if you compare the electrons moving down this first light bulb branch, they're moving pretty quickly. These are moving not as fast, which means there's more resistance in this resistor than there are in this light bulb. And when I click the last switch, this bulb isn't as bright, which means it has more resistance in this filament up on top than the other light bulb when we first started. So we're going to go ahead and measure some voltage along the way. The battery should be at 12 volts, which it is. And one of the rules for parallel circuits is that every branch has the same energy source. So the electrons will choose the path of least resistance and travel the fastest through them. So when the electrons are moving slow at the top, the resistance is high. Medium speed, medium resistance through the middle. And fast moving electrons, high current, means that we have low resistance here. So I'm going to click the values to show you those numbers. We have 60 ohms, no resistance through the wire. We have 20 ohm resistor, and we have the lowest 10, most current with the lowest resistance, slowest current with the highest resistance. So if we go ahead and we check how does the voltage change as we go across each branch, we find out that it's the same. Well, they're all being powered by the same battery, so that kind of makes some sense. And when we go ahead and move it up, the resistor has, again, 12 volts, and the light bulb up on top, 60 ohms, but the voltage, if I can get this wire out of the way, is still 12 volts. So 12 volts constant for every branch in a parallel circuit. So let me move the voltmeter off. Then I'm going to make use of the ammeter. So if the volts are constant, we have 2 amps coming in and out of the battery. 2 amps. But each branch has different traffic flow patterns. So if you have multiple ways to drive and pick a route, you don't want to pick the one that's backed up. You want to pick the one where things travel fast. And we have the highest current, 1.2 amps, going through the fast-moving branch. The medium, 0.6 amps. And the slowest moving up at the top has only 0.2 amps. So if we're going to try to use some physics to make predictions using Ohm's law and Joule's law, we're going to go ahead and switch to our schematic diagram showing resistors in squiggly lines, light bulbs with these circles, and the battery with the parallel lines. And that will let us go ahead and try some math with this so we can make predictions on how this circuit should work. Now that you've seen a parallel circuit, we need to work on the physics, so here comes the math. The math is a little trickier with the parallel circuit since we have to add the reciprocals of each individual resistor on each branch to find out the reciprocal of the equivalent resistor in parallel. So using our example, we have 1 over Rp equal to 1 over 10, one of the resistors we had in our circuit, plus 1 over 20, plus 1 over 60. Using the common denominator, this turns into 6 over 60 plus 3 over 60 plus 1 over 60, giving us 10 over 60, which reduces to 1/6. When we take the reciprocal of that, we find out the equivalent parallel resistor would be 6 ohms. So now that we figured out that the equivalent resistance is 6 ohms, we'll place that in our RIVP table, the top left. We know the battery is still 12 volts, so using Ohm's law, we can figure out there must be 2 amps of current. We can then figure out the amount of power used. 2 times 12 will be 24 watts. The real circuit we used had a 10, 20, and 60 ohm resistor. So we're going to fill those in for the actual resistors of the circuit. Remembering that every branch in a parallel circuit has the same voltage, we're going to make sure each of those have 12 volts. Now we need to use V equals IR and P equals IV to complete the missing blanks of our table. For the 10 ohm resistor, we need to multiply by 1.2 amps of current in order to get our 12 volt drop for that branch. Same thing with the 20 and the 60 ohm resistor, giving us 0.6 and 0.2 amps of current. Then we want to figure out the power using I times V. So 1.2 times 12 gives us 14.4 watts. 0.6 times 12 gives us the 7.2 watts. 0.2 times 12 gives us the 2.4 watts used by that branch of the circuit. So you can always check your work on any of these using the table. So since we didn't drop I down, we calculated those. Those numbers should add up to the equivalent resistance for the entire circuit. So if we had 0.2, 0.6, and 1.2, we've got the correct 2 amps of current flowing through the circuit as a total. We can also check the power numbers by adding the 3 calculated values, 2.4, 7.2, and 14.4, giving us the 24 watts used by the entire circuit. Now that we've done both series and parallel circuits, we've got a couple things to review and compare between the two. Here's a T-table that shows the major features of a series and parallel circuit. Pause the video to jot these down if you need to take notes. The rules that you just learned about how to solve series and parallel circuits will be key in understanding how to solve more complex circuits. So I'll see you next time.